Chapter 9, Prop 25. A man doing push-ups pauses in the position shown in figure 965. His mass M equals 68 kilograms. The question is, determine the normal force exerted by the floor, A on each hand and B on each foot. So here's my drawing of our guy doing push-ups. So a few things I just want to point out first is that you should focus on making a free body diagram of this, or at least including arrows like this. So we're going to have the hands here, of course, feet here, and then the center of mass just in the middle. But we're actually only going to, we normally would use mg if we wanted to find the, the force of both hands and feet, but since we just want to find it on one, then we want to use half. I also want to take counterclockwise torques as positive and take the pivot to be around the feet. So we'll go around here, this is positive, and then this will be negative. That just means that whenever we do our sum of the torques, whenever we use sum of the torques, sum of the forces equals 0 because we're in equilibrium, mg is going to have a positive coefficient, and force from the force on the hands are going to have a negative coefficient. So it just looks like this: half mg times the distance it's at. So half mg times the distance it's at, fh times the distance it's at, which is just d1 plus d2, and then half mg's distance was d2 away. You just plug all that in, do algebra, and you get that the force on the hands should be about 230 Newton. Similarly, for the second part, you can do sum of the forces and look at the y direction specifically. So we have the force on the hands and the feet going up and just half mg going down. You could also write this, if you want, as 2fh plus 2ff minus mg. It's the same thing, just multiplied 2 all the way through, but it's not that important. Doing algebra, you just get 100 newtons